Okay, welcome to class for, I guess it's Wednesday, April 22nd. Today we're talking about torque. All right, reminders. For Wiley Plus, this week you should be working on the Chapter 10 homework and adaptive practice, as well as Chapter 7, 8, and 9 before it. For perusal, the next perusal reading is due next Wednesday. It's on harmonic motion. And video experiment 7, for which covers moment of inertia, is available now online. I did want to note that there's more than one data set, more than one trial in the data that that comes with that. So please look at more than one. Look at all of them. You should remember to sign up for a final exam slot. The final exam will be oral. It'll be the week of finals, and you need to sign up for a time to meet with me to have your exam discussion, whatever you want to call it. And then just as a note, I'm starting to get a little nervous here because everything, and I mean everything, is due Friday, May 8th. And there's a lot of stuff that hasn't been turned in yet, which is making me a little nervous that you guys are all, or not all, but some of you may be procrastinating a bit here, and it will not go well. So if you have been procrastinating a little bit, now is the time to change that pattern, because trying to do everything that's due for the whole semester, the last week of the semester, is going to go really poorly. And then just the standard reminder that I'll be on after this, after class officially ends, for questions, comments, concerns. And Sean has office hours tomorrow from 11 to 1 at the same Zoom link that you guys can take advantage of. All right, questions about any of this stuff?
About the Wiley Plus homework, I think that 2 due dates have passed since I did my chapter 9, and I still don't see my grade for the homework or the adaptive practice in the grade book.
I'll have to look at that. I'm not sure what it's doing there.
We can do that after class.
Yeah, I'll have to take a look at that. I don't know.
Mm-hmm.
As I've said before, the Wiley Plus system is a little new to me and does not make a whole lot of sense in some ways. It won't comfort you guys at all any, but I've pretty much decided I'm not using Wiley Plus in the future. Actually, I'm hopeful I never have to use online homework ever again. But, here we are. Okay, any other questions? I'll look into the Wiley Plus grading thing. Oh, okay, let's talk about actual physics. So, as I said, today we're talking about torque. So hopefully you read about torque in the perusal reading. And so here's our question about this. You've got a choice between 2 screwdrivers. Their handles are identical, okay? So assume that the handles of the screwdrivers in those pictures are exactly the same, okay? But one has a length of 10 centimeters and the other a length of 50 centimeters. Which would allow you to apply more torque to a screw?
Are we assuming that the screwdrivers don't twist at all? Like the shaft doesn't twist?
Yeah, I mean, you use it like a screwdriver. You're not going to bend the shaft.
It depends on how hard you crank on it.
Yeah, so we're gonna assume you're not going to bend the metal.
Thanks.
All right, I'll give you another 10 seconds. All right, going once, going twice. Sold. Okay, so the most common answer was C. C is the right answer. So why doesn't the length of the screwdriver matter for how much torque you can apply to a screw?
It's because the screwdriver is not being used like I guess perpendicular to the head of the screw, not like if you're twisting up or down like lug nuts on a car.
Yeah, because a screwdriver, you're twisting it around the handle, right? If you're using it to twist a screw, right? Yeah,
Yeah.
if you were using it as a pry bar, then this would be a different question. But the length the length of the screwdriver doesn't matter. And it's exactly because of what Lewis says, is that in what matters here is the perpendicular distance, right? So the perpendicular distance between where the force is applied on the edge of the handle of the screwdriver, right? And where it's rotating about. Now, if you're using a screwdriver like a screwdriver, right? It's rotating about the center of the handle, right? The screwdriver is rotating about a line that goes through the length of the screwdriver. And so the width of the handle will change the amount of torque you can apply, but the length of the screwdriver doesn't. And that gets at something that we'll hammer on a little more here, that when we talk about torque, there's a cross product involved. So let's do one more of these and then we'll talk a little more about it. Okay, so let me relaunch the poll. Okay, well, hold on. Before we do this one, let me actually just respond. So Thomas said in the chat, wouldn't it only be affected by distance away from the turning axis with your hand? That's exactly right. All right, so here's your next question. Can you guys see the window, the polling
Yes.
window? All right. So you've got a kid who's pushing a merry-go-round on a playground. That causes an angular acceleration of the merry-go-round of half a radian per second squared. If the merry-go-round started from rest, how long did the kid have to push for the merry-go-round to complete 4 revolutions? Okay, I'll give you another 10 seconds here. Going once, going twice. Sold. Okay, most people said C. Anybody want to argue for C? Come on, I know somebody wants to argue for C. Please, oh, please, oh, please.
I took a guess.
All right, we'll have a guess at C. Anybody have an argument for C?
So I did this using like kinematics kind of. I don't know if that's the right term for angular stuff.
That's exactly the right term.
I solved for position using the acceleration. So it was 4 revolutions is 8 pi, I believe.
That's right.
So I set 8 pi equal to 0.5 over 2 times t squared, and I solved for t. That was about 100. What's the square root of 100?
Very nice. Did everybody follow that? All right, let me write it out. Hold on. I got to remember how to do that. All right, I'm going to stop sharing. I'm going to change my video. Hey, there's my video. Okay, so what Joel was saying there was that he took that this was just a kinematics problem, right? Except for instead of being linear acceleration like we did at the beginning of the semester, now we have an angular acceleration of 0.5 radians per second squared. Well, if we know that the acceleration, we can integrate that to get the angular velocity. So the angular velocity is just going to be the acceleration times time plus my initial angular velocity, which is 0 because it started from rest. Okay. And then I integrate it again and I get that my angle as a function of time is 1/2 my acceleration times time squared. I don't have to worry about the initial angular velocity times my initial angle, which again, I can just call 0 because I can say it started at 0. I can put my 0 wherever I want. Okay, so now it's just a question of solving for t. Solve for t, I get that t is 2 times theta over alpha square rooted. If you plug in some numbers, 2, this is the square root of 2 times.
My pencil.
I'm sorry, what was that?
Oh my god.
Okay, so we wanted to go through 4 revolutions. 4 revolutions is 8 pi radians. So I've got 8 pi there, and I'm dividing by my angular acceleration, which is roughly 1/2, which is exactly 1/2. And when I do that, I get the square root of 2 times 8 is 16, divided by 1/2 is times 2 again. So I've got 32 pi. Well, 32 times pi is really close to 100. So this is about the square root of 100, which gives me 10 seconds. So this is exactly the same as the kinematics we were doing at the beginning of the semester. It's just now we're talking about rotating things instead of talking about linearly moving things. We're talking about things spinning instead of things just going in a straight line. So we use these weird alpha, omega, and theta instead of A, V, and X. But it's the exact same thing. Okay. Okay. Oh, go ahead.
How did you get the 8 pi?
8 pi. How did I get 8 pi? Because I wanted 4 revolutions, right? So 4 revolutions is 4 times all the way around a circle. How many radians are there all the way around a circle?
2 pi.
2
radians.
pi. So 4 revolutions is 4 times 2 pi radians, which is just 8 pi radians.
And
Does that make
so,
sense?
yeah, so whenever we get a problem with revolutions in it, we have to convert that to radians.
Right, because radians is the easy way to do this, right? If we want to talk about angular acceleration, angular velocity, and angle, all in the same sensible units, we want to do it in radians, not in revolutions. Now, interestingly enough, we could actually do this problem because we never had to convert to anything in terms of a distance. We could have done it in revolutions. So we could have come up here and said, okay, well, alpha is 0.5 radians per second. How many revolutions per second is that? And we would have gotten that this is, let's see, we would divide by 2 pi. So we would get 1/2 divided by 2 pi revolutions per second. Okay. Which is kind of weird units, right? But it actually would have come out exactly the same, because instead of putting 8 pi in here, we would have put 1/2, we would have put 4 in there and 1/2 divided by 2 pi in the denominator. It would have come out mathematically exactly the same. But to be safe, I recommend always work in radians, because if you always work in radians, you'll never have a conversion problem. Okay. If you work in revolutions, sometimes you won't just be able to do like your angular acceleration times your radius equals your linear acceleration. You'll have to think about that a little more. Okay. Does that make sense?
Yeah, thanks.
Great. All right. So now here's the follow-up question to this one. We figured out how to deal with the angular acceleration once we have it. Now, let's think about this in terms of torque. For that same merry-go-round, which is approximately a solid disk with mass m, an angular acceleration of alpha, and a radius r, the force applied by the kid must be which of the following? Let me relaunch the poll. All right, you should be able to see the poll. Okay, I'll give you another 10 seconds here. All right, going once, going twice, sold. All right, interestingly enough, nobody likes D, but We got the same number of votes for A, B, and C. So let's talk about this one. Let me come back over here. And we'll work on this one. Okay, so in the reading, you should have read about a different way or the rotational version of Newton's second law. What's the rotational version of Newton's second law? So let me put a line down my paper here. And let's write, so here's our linear world. That's where we've lived all semester. And here's our angular world, right? So for example, Newton's second law in the linear world is either written as the sum of the forces equals mass times acceleration, or equivalently, it's the time derivative of momentum, right? And there are other things. In the linear world, we talk about acceleration, velocity, and position. In the angular world, we talk about angular acceleration, angular velocity, and angular position. Okay? In the linear world, we talk about linear kinetic energy. In the angular world, we talk about rotational kinetic energy. Okay? In the linear world, we talk about mass. In the angular world, we talk about moment of inertia. So what goes up here? What's the angular version of Newton's second law? Well, what's the angular version of a force?
Torque.
Torque, right? So down here we could put force. Here we could put torque. And we usually write torque as a Greek letter tau, which is just like kind of this weird curly T thing. Okay? Okay, so the angular version of Newton's second law, if we just follow the example from the linear one, should look like the sum of the torques equals what? What's the, say that again?
Moment of inertia
Moment of inertia.
times alpha.
Yep, times our angular acceleration. This is the rotational version of Newton's second law. What this tells us is that in order to make an object's spin change, right, to make it start spinning or stop spinning, we need a net torque, right? And you know this. Anyone who's ever used a screwdriver knows this. You have to apply a torque on a screwdriver in order to make the screw spin, in order to make it experience an angular acceleration, in order to make it start spinning, right? Now, usually we don't have a problem with things stopping spinning when we talk about screws because there's an awful lot of friction on them by design, right? They're usually pushing into wood or metal or concrete or something, okay? But anyone who's ever played with a fidget spinner knows that it does take something to stop one of those things, right? Once you get them spinning, they don't want to stop by themselves. So if you want to stop it, you need to apply a torque. And just like mass played the role over here of the thing that prevents things from accelerating, right, or slows them down, limits their acceleration, that's exactly what moment of inertia does as well. Moment of inertia is the quantity that resists angular acceleration. By the way, there's also an angular version of this piece. Anybody want to guess what that is? If the forces change momentum, torques change something called angular momentum. Okay? And just like momentum is this magical conserved quantity, right? You can't get rid of it, or you can't create it, you can't destroy it. All you can do is trade it off between objects. Angular momentum is exactly the same way. Okay? Unfortunately, we just don't have time this semester to spend as much time on angular momentum as I'd like. But you should all become physics majors and come take my junior level class, and you will see a lot of angular momentum, and we will have a great time. Okay, so Newton's second law for angular form is the sum of the torques equals your moment of inertia times your angular acceleration. Okay? So this begs the question, then, if we want to go back to our merry-go-round problem, how do I relate the torque to the angular acceleration? Right? Well, I know that. So if the merry-go-round is a disk, right? A disk has a moment of inertia of 1/2 mr squared. And there's our angular acceleration. And we're going to say we only have one torque. Now, you almost always have torques due to friction. This is why ball bearings exist. Okay? There are ways to reduce friction for rotating objects. But you almost always have some friction. But we're going to ignore that for now. We're just going to worry about what the kid did. So the torque applied by the kid has to be 1/2 mr squared times alpha. Okay? Now, we've got to ask ourselves something here. And that is, how do we relate torque to force? Because what was actually asked here was how much force did the kid have to push with? So, in this case, we can draw a little diagram here. And we can say, okay, the kid's pushing out here with some force. And here's our radius vector. Which way is that force going to want to make this merry-go-round spin?
In the positive direction. So
By positive, you mean
counterclockwise.
Counterclockwise or up, right? Now, it's weird to say that, right? But really, that's the direction it wants to spin. It wants to spin up. It wants to have an angular acceleration in the upward direction. Now, that's weird because nothing's actually moving up. But the right-hand rule, right? If I take and we'll talk about this more, right? If I apply a force this way, it's going to want to spin that way. I curl my fingers. That means my angular acceleration is up. So my torque is actually my force times my radius because they're perpendicular to each other. And, oh, actually, you know what? I have a mistake on my slides. The right answer isn't even there. Oh, good job, whoever said E. So the force, I can cancel one of these R's on each side. The force required is actually 1/2 mr squared alpha. So good job, whoever said E.
Unless I'm misunderstanding this, the R squared that canceled,
Oh,
so it should just
I'm sorry. It should just be R. You're right. You're right. No squared. So it looks a lot like C or D, just with the 1/2 and the 1/2 instead of a 2. Okay. By the way, just as a test taking strategy in general, one of the things you could do here is check units, right? So if you want a force, you better have units of newtons. What is a newton?
Kilogram meters per second squared.
There you go, kilogram meter per second squared. So there's my kilogram, there's my meter, and that is radians per second squared. Remember, radians are unitless. So this is kilogram meter per second squared. So this has units, this piece right here, right? This answer has units of newtons, okay? C and D also had units of newtons. A and B had units of, I don't know, something else, right? But not newtons. Okay, so let's talk a little bit about this, because torque is the first time we really have to think hard about this cross product business. A torque is defined as the cross product of a radius vector and a force vector, okay? So torque is the result of a cross product. Now, we've talked about cross products before when things are perpendicular to each other, right? When things are perpendicular to each other, we just use the right-hand rule to get the direction, and then we just do this as R times F, the magnitude of the radius times the magnitude of the force. But what if they're not perpendicular to each other? What then? Now we have to worry about things. Okay, so let's suppose that I have a wrench, right? I've got some wrench and I have some nut, and I'm only going to draw a square because it's easier. And I have a wrench that is shaped kind of funny, right? Here's my wrench. And the handle comes off at an angle, okay? You see these sometimes. Okay, so I apply a force here on the ends straight down. There's my force. I'm trying to spin the nut. So where is my center of rotation?
The middle of the nut.
The middle of the nut, right? So I need to draw a radius vector. I draw a radius vector from the middle of the nut out to where I'm applying my force. And there's my radius vector. And those are not perpendicular. Okay? So now what do we do? Well, anybody will tell you, which way is this going to make things spin?
Counterclockwise.
Really?
Clockwise.
Clockwise. Yeah, this way. It's going to make
Yeah.
you spin this way, right? Okay, and we can check that with our right-hand rule, right? It's going to make it spin that way. So that means it's going to be pointed into the page, okay? But now we have to worry about what to do with this because they're not perpendicular to each other, okay? So when they're not perpendicular to each other, now we have to worry about this cross product, okay? It turns out there are 4 ways to do a cross product. They all work. Some of them are easier some of the time. Some of them are easier at other times. Okay, but they're all equivalent. So the first thing to do is now we have to do the right-hand rule in earnest. Okay, so the way you do the right-hand rule is you take your fingers and you put them in the direction of the radius vector. Okay, and then you curl your fingers towards the direction of the force vector, and your thumb will point in the direction of the torque. Okay, I have a diagram for this. Let me come over here to my diagram. Because this is hard for you guys to see. This is one of those things that we really should just all be in the same room. But this is the idea, okay? You have your radius vector here. You draw your radius vector from the center of rotation out to wherever your force is being applied. And then you take your fingers and you point them along the radius vector. You curl your fingers so that they move towards the force vector, right? And your thumb will point in the direction of the torque vector. Now, be sure to use your right hand. If you use your left hand, you'll get everything wrong by a negative sign. So Does that make sense to everybody? Unfortunately, this is an inherently three-dimensional thing, and I can't show you it in 3 dimensions. I can only show you drawings that are supposed to look three-dimensional. Okay? So we'll just do the best we can here. But the idea here is that the right-hand rule tells you the direction of the torque. It doesn't tell you the magnitude of the torque. So we're going to actually have to take the cross product in order to get that part right. Okay? Okay, so let me come back over here. And let's talk about 4 ways to do the cross product. Okay? Way number 1. To get the magnitude of the torque, we're going to take the component of the radius that is perpendicular to the force vector and multiply them together. So if we come down here to our drawing, which component of the radius vector is perpendicular to the force?
The one in the x direction.
Right, because my force is straight down. So the radius component I want is the horizontal bit. So I need to break this thing into components, right? I need to draw my triangle, and it's not a great triangle, but you get the idea, right? So here is my Rx, and here's my Ry, which is my perpendicular components, okay? Which means I need to figure out how much of the radius is in the x direction and how much is in the y, okay? And let's suppose I was given that, right? So I know, let's say I know this angle right here. I know that the radius vector is some angle theta from the horizontal, okay? Well, I can use a little trig, come down here. That means this angle also has to be theta, which means I want R, the magnitude of R, times sine theta in order to get this thing. So my torque is going to be R times F times sine theta. Okay? That's way number 1. Here's way number 2.
Were you trying to get RY or RX?
I was trying to get RY. Okay? Does that make sense?
Why? I thought you were trying to get the one perpendicular. Wouldn't RX be perpendicular?
Oh, I'm sorry. You're absolutely right. You're absolutely right. I want the perpendicular components. So the way I've drawn it, this would be cosine theta because I want Rx. You're absolutely right. Good catch.
Yeah.
Okay.
If not, it would have been parallel RY.
Yes, because Ry is the one that's parallel, and that's the one that doesn't matter. Okay, now, way number 2. I can find the component of the force that is perpendicular to the radius. Okay, to do that, I'm going to do something fancy. I'm going to rotate my paper so that now my radius is all in one direction. And now what I have to do is break up my force vector into components. Okay. So here is my new, I'm going to call this F perp, and I'm going to call this F parallel. Okay, the nature of my angles hasn't changed. And so what I'm going to do here is realize that, okay, I drew it poorly, but this arrow should actually point all the way to the end here, okay? Which means that since this is a right angle, that this guy, again, over here has to be theta, okay? So the perpendicular component of F is just the magnitude of F times cosine theta. So I get R, F, cosine theta. Okay, way number 3. Way number 3 is we just say that the torque is equal to your magnitude of your radius times the magnitude of the force times the sine of the angle between them, which I'm going to write as phi. Okay? For me, this one is conceptually hard because I never know which angle is the angle between them. Okay? But one way to figure it out is to extend your radius vector out, and this angle here is the angle between them. Okay? Now, if we continue this, we'll see that phi and theta have to add up to 90 degrees.
You're off the page.
Oh, sorry. Let me scoot up a little bit. Is that
Thank
better?
you.
Okay.
Yeah.
So phi and theta have to add up to 90 degrees. So sine phi is just, so my torque is RF times the sine of 90 minus theta, 90 degrees minus theta. Okay, and if you remember your trig, the sine of 90 minus theta is just the cosine of theta. Okay. All right. There's one more way to do this, and it's the way that always works. Okay. So when in doubt, or when you get confused, this is the one to go to. By always works, you can also probably guess it's going to be the messiest. Okay. So method number 4 involves taking the determinant of a matrix. How many of you have fond memories of somebody telling you to take the determinant of a matrix at some point in your life?
The calculator can do it if you know the matrix, right?
Exactly. Yes, your calculator can do it. So
isn't that linear algebra?
Yes, it is linear algebra. So here's what we're going to do. We're going to write out R in components. Okay. So R is just Rx, Ry, and 0, because there's no component of the radius going out of the page. Okay. We're going to do the same thing with our force vector. Our force vector, well, it has no x component. It has a y component, Fy, and it has no z component. The torque vector is equal to R cross F, which is equal to the determinant of a matrix where I'm going to put x hat, y hat, and z hat on the top row. I'm going to put the components of R on the second row, Rx, Ry, 0, and I'm going to put the components of F on the third row. Okay, and now I get to take the determinant of a matrix. Okay, your calculator can do this with numbers. It will not do it with unit vectors, but you can do this fairly easily if you remember a little trick here. Okay, so imagine that this matrix is like a wraparound thing, like in Pac-Man. You know, you go off one end of the world, you just come back on the other end. Okay. What I'm going to do is, starting at the top, I'm going to make diagonals moving to the right, positive, and diagonals moving to the left, remembering that if you go off the edge of the world, you just come back on the other side, negative. So if I take this whole thing apart, I get x hat times Ry times 0, right? That's this diagonal. Minus, now I do the negative diagonal. X hat, go off the edge of the world, come back over, times 0, times Fy. Okay, now I move on to the y, and I do the exact same thing. I do plus y hat, 0, I'll go off the edge of the world, come back on the other side. So 0 times 0. Okay, and then the negative y hat 1, I go negative y hat rx, go off the edge of the world, come back, 0. Okay, now I've got to do z. So I'm just going to keep going. Plus z hat, go to the right off the edge of the world. So I get rx, fy, and then the negative version of z hat, ry 0. Okay, like I said, it's cumbersome, but it's always right. And now here's the cool part. I don't even have to do the right-hand rule. I already have the vector form of the torque, right? The torque has the vector form. Well, there's nothing in the x because they both have zeros. There's nothing in the y. They both have zeros. And in the z, this one has a 0. So all I've got left is this positive term of rx fy, which, as we already showed, is equal to 0, 0, r f cosine theta, right? We already figured out what rx times fy was. Okay, so there are 4 ways to take a cross product. Which one is the best? Well, that's not really the right question. They're all useful at different times and in different ways. Which one would you prefer to use? I don't care. They will all work. Some of them will work more easily than others at certain times. So if we go back to our drawing here, I drew this angle here, but it turns out that's not the angle I wanted to do this trick, right? To do RF times the sine of the angle between them. So be careful of that. There's nothing that guarantees that the angle you're given in the problem is the correct angle for this method. Okay? This is the one I like to use. This R perpendicular is often called the lever arm. Okay? It tells you the radius perpendicular to the force you're applying. Okay? Which is often a useful thing. It's often a conceptually easy thing to figure out. For me, anyway. Which one do you want to use? I don't know. Whatever floats your boat. But in all of them, we're going to have to play this game, right? We're going to have to play this game where we have to, you can't just do the radius times the force unless they're perpendicular. Because if they're perpendicular, the angle between them is 90 degrees, and we just get radius times force. All right, questions?
If you know how at first you were gonna use for the first one RF sine theta, it would have worked like the way I first do the triangle. I drew my triangle on top, like the second half. So wouldn't it be equivalent?
If you drew this triangle, you said?
Yeah. The RX down at the bottom would be the same RX at the top.
Yep. So this is RX and this is RY, right?
And then in that scenario, it would have been sine theta.
Nope, because sine theta is RY.
Right?
Right?
Oh, never mind. So it's the
Still
same
cosine.
thing.
Yeah. So now, if I had called this angle theta, right? If I had said, oh no, this angle right here is my theta, now theta would be what you wanted for this third method here, right? But you should be careful on that because, like I said, there is nothing guaranteeing that the angle you're given is the one you want, is the angle between the vectors, whatever that means, right? So be careful of that. Just a thing to be careful of. The way you can usually check, and this works for me most of the time, is I just extend the radius vector and then that's the angle right there. That's the angle you want for this method, okay? But be careful of that. This is the kind of thing that you just need to practice, right? There's no way to always get it right from the beginning. You just need practice, okay? All right, so let's do a practice question with this. Let's come back over here. I'll share my screen. Okay, so here's your question. You've got a mass hanging from the end of a horizontal bar, which pivots about an axis through its center, but is currently being held stationary. The bar is released and begins to rotate. As the bar rotates from horizontal to vertical, the magnitude of the net torque on the bar increases, decreases, or remains constant. All right, I'll start the poll. All right, I'll give you another 15 seconds here. Going once, going twice, sold. Okay, here's what I want to do. So most people said B, most people are right. What I want you to do, you should be able to draw on this screen, okay? So if you go up to annotate, or maybe it's, I think it's annotate is what you want. Do you guys know how to draw on the screen? Yeah, there you go. Somebody's drawing on the screen. Okay, so here's what I want you to do. I want you to draw the radius vector that matters here. So somebody grab an arrow on the draw option and draw me the radius vector. There we go. Okay, so we've got a radius vector, right? It starts at the, hold on, there we go. It starts at the center of rotation and it goes to where the force is. Okay, now somebody else draw me the force vector on the bar. Luis, are you saying the force is sideways on the bar? There we go. Okay, downward, right? There we go. It's a downward force on the bar. Okay, so which way is the torque? This one you can't draw because, well, we'll see in a sec, but which way is the torque? Well, to figure that out, we can use the right-hand rule, right? We can take our fingers. So take your fingers, hold them up to your computer screen. You'll feel like a dork. It's okay. Just embrace it. Okay? You hold your fingers up in the direction of the radius, and you curl them the direction your force is pointing. Okay? So here, let me switch. Well, I can't do that. Okay. So I'm holding them up, and I want my fingers to curl downward, right? Because I want them to curl in the direction the force is pointing, which means that my torque is pointing towards my face, right? My torque is pointed out of the screen. That means the bar is going to rotate counterclockwise, which is, of course, what you already knew, right? Just looking at this, you knew that that bar would want to rotate counterclockwise. Every kid who's ever been on a teeter-totter knows that the heavy side goes down, right? So our torque is going to be downward. Now, why is it going to decrease as it swings downward?
Because when it's at 90, which is right there, that scenario that we have, that's its maximum torque. So anything in between from there till where it's at 270 degrees is decreasing.
Okay, so he's saying the angle between the two vectors is going to change, right? Because remember our formula, we take the magnitude of the radius times the magnitude of the force times the sine of the angle between them. Well, sine is at a maximum for 90 degrees. But once it starts to swing, that angle is going to get bigger than 90 degrees, which means our magnitude of that torque is going to start decreasing. Okay, another way to think of this is my lever arm is going to change, right? The component of the radius that's perpendicular to the force is going to change as the bar rotates, okay? The force is always going to be downward, and right now the radius is all to the left. But as the bar starts to rotate, that radius is going to change until eventually it's pointed straight down. And when it's pointed straight down, there's no component of the radius that is perpendicular to the force vector, which means you get no torque, okay? We could also do this with our second method, right? We could say what we want is the component of the force that's perpendicular to the radius. And as the bar swings, the radius of the bar is going to change, right? Direction, which means that there's the component of the force that's perpendicular to that radius is going to shrink. Okay? So there's just a whole bunch of these, right? We could even do this with the the determinant of the matrix thing, right? Now that's probably overkill here, and it's a lot of algebra, so we won't mess with it. But you could do it, right? It would work. All right. Questions? Okay, let's do one more example. Hold on, I gotta clear this thing off. There we go. All right, so let's do the one where you do that everyone who has ever changed a tire has probably done. Okay, you're trying to change a tire and the lug nut is stuck. So what you do is you get a big old wrench, like a tire iron, and you stand on it, right? Because that's about the best you can possibly do to try to get that thing unstuck, okay? So Frank gets the tire iron. The tire iron has a radius of 0.26 meters, and he stands on it, which just barely causes it to turn. Frank has a mass of 75 kilograms, and the lug nut has a radius of 2 centimeters. How much force was whatever caused the lug nut to be stuck applying on the lug nut? Okay. So let's come over here. I'm going to stop sharing my screen. And let's come over here and work this thing. So all right. So here's our lug nut. Okay. And here's our wrench that goes around the lug nut. And here's the tire iron that goes all the way out here. And here is Frank's foot. Okay. All right. So we know that the radius vector here, right, is the distance from the center of the of rotation, which we want to be the center of the tire or the lug nut, all the way out to where the end where Frank is stepping on it. Okay. So I'm going to call that R Frank. Okay. Okay. Frank is applying a force, which presumably is downward, right? That's just equivalent to his weight. Okay.
Wouldn't the diagram have to be flipped if he's trying to take the lug nut
Oh,
off?
you're right. You're right. Because I made this so that he's putting the lug nut on. Yeah, okay, let me start over. Good call. Otherwise, it's a left-handed lug nut. All right, so here's our lug nut. Here's our wrench. Okay. Here's our tire iron coming all the way out here. Okay. Oh, dang it. I did it again. All right, we can solve that. There we go. Flip it over. Okay, so my radius vector, can you guys see that? My radius vector goes from here to where the force is being applied, and we've got Frank's foot. Okay, applying a force. Oh wait, this is our force, right? So this is the weight of Frank, and this is our Frank. Okay. Okay, so why isn't the tire iron experiencing a huge angular acceleration right now? We said it's just barely starting to move.
Because the lug nut is super tight.
Yeah, because there's some other force here. There's some other torque. Okay, I'm going to draw it in blue. And it goes from here to the radius of the lug nuts. Okay, so here's our little teeny R lug nut. Okay, and it's got some force. Now, which direction is the force? Well, to do that, we're going to have to figure something out here. Okay, which way is Frank trying to get the lug nut to turn?
Counterclockwise.
Yeah, counterclockwise, out of the page, right? And we can figure that out using the right-hand rule if we put our fingers in the direction of R and we curl them in the direction of F, our weight, we see that our thumb points out of the page, okay? So the torque from Frank is going out of the page or counterclockwise. And I like to draw that this way, okay? I like to say that my torque, and then I just draw a little arc with an arrow on one end that shows which way we're rotating. So that means that the friction force or whatever, gunk or rust or whatever it is that's holding it on has to be making a torque. We'll call it friction. Oh no, I already used F for Frank. Lug nut has got to be going the other way, right? It's got to be going clockwise. So if I draw my radius vector to here, which way does the force have to be? And how would we figure it out?
What do you mean, like the force?
So there's a force on this lug nut, right? That's resisting Frank from rust or grime, or just because it was tightened down a lot, right? But there's some kind of friction force here that's resisting Frank trying to move it. There has to be, right? Otherwise, this thing would spin like crazy when Frank jumped on the tire iron.
So you're asking, where is this force pointing?
Yeah, where's the force pointing and how do we figure it out? So the way we figure it out, well, somebody want to take a shot? All right, so let's use our right hand rule, okay? We know that we need our torque to point down into the page, right? Because our torque is going to spin the opposite direction that Frank's trying to spin the lug nut, right? It has to be resisting. So it's got to be opposite, which means I need my thumb pointed down and my radius vector is pointed across this way on the page, right? So my thumb's pointed into the page, my radius vector's up. Which way do my fingers spin?
To the right.
To the right, which means that force would have to be pointed this way. The force from the lug nut would have to be pointed that way. Now, in reality, the force on this lug nut probably isn't coming from one spot. It's probably coming from a ring around the edge, right? So there's probably another force down here pointed to the left, right? On the bottom of the lug nut pointed to the left, because its R would be down, right? R down, F is to the left. That gives me the torque in the right sense. And I can do that all the way around the edge of the lug nut, okay? All right, so Newton's second law, the rotational version, says that the sum of the torques equals your moment of inertia times your angular acceleration. If your bolt is just barely starting to move, what's your angular acceleration?
0.
0, right? Just a smidge above 0, okay? So if it's 0, then all we know is that the sum of our torques equals 0. Okay, we have two torques here. Which way do you want to call positive? Do you want to call out of the page or into the page positive?
Counterclockwise.
Counterclockwise. So out of the page, right? Out of the page is going to be our positive, which means we have our torque from Frank minus our torque from the lug nut equaling 0. Okay? And now all we have to do is take these apart. Now, conveniently, both of these torques are made up of radius vectors and force vectors that are perpendicular to each other, right? So I don't have to play any games with sine of angles or figuring out the perpendicular components. I can just say that the torque from Frank is the radius at where Frank's applying his force times his weight, and the torque from the lug nut is just the radius where the lug nut is applying its force times the force from the lug nut. And if I solve these things, I don't know what the force of the lug nut is, so I solve for that. Force of my lug nut is just R Frank times Frank's weight divided by the radius of the lug nut. Frank's weight is just his mass times gravity, so I end up with R Frank mg over R lug nuts. Okay? So what if we plug in some numbers here, right? Okay, so I said the radius of the length of the tire iron was about 1/4 of a meter. So it's about 1/4. It's approximate. Oh, I said a quarter and wrote a half. 1/4 of a meter times his mass, which is 75, or 3/4 times 100, times G, which is 10, all divided by 2 centimeters, or 2 over 100. Okay. Or I could just all plug this into Google, but I don't want to stop to plug it into Google. So if I do the multiplication out, I get in the numerator, I get 3/16 times 1,000 divided by 2 over 100. The 100 comes up to the top. The 2 will go into the denominator. So I get 3 30-seconds times 100,000. Or in other words, approximately 3 30-seconds is approximately a tenth. I approximately get 10 kilonewtons. Okay, or 10,000 newtons. Okay, that seems insane, but that's actually an accurate value for this problem we just worked. Okay, why on earth could your lug nut have so much force? So much friction force?
Rust and just it's been sitting under and heat.
Yep.
It causes it to like stick.
Yep. So what's happened here is that there are chemical bonds that have been formed between your car, between the threads and your lug nuts. They've been so close to each other, and they've been warmed up and cooled down so many times, and you've had things like chemical processes like rust going on. You've actually formed chemical bonds between your lug nut and the threads, right? Which means you have to physically break material in order to get them off. Okay, that's why you sometimes hear getting it loose is called breaking the nut, right? You are literally breaking these chemical bonds that have formed. So which can be incredibly strong, right? 10 kilonewtons. That's a lot of force. Okay, so let's stop here for a second and let's review. What we've really focused on today is this concept of torque. That torque is the thing that makes things rotate, or better yet, makes things change how they're rotating. So if you want to change the way something's rotating, you have to apply a torque. Okay? You have to, and to apply a torque, you need a force applied at some distance from the center of rotation, and the force needs to be perpendicular to, or a component of the force needs to be perpendicular to that radius vector. Okay? Now, the cool thing about this is all stuff you know. Anybody who's ever worked with a wrench has an intuitive understanding of torque. Now we want to make it a mathematical understanding. That's the goal for this section. We want to take what you already intuitively know about torque, and because you've worked with screwdrivers and wrenches in your life at some point, and we want to change it from just a feeling, right? You know it because you feel how things work, to somewhere where you can actually calculate it and you can get quantitative numbers out of it. Okay? Why would it be important to get quantitative numbers out of it?
So you won't break bolts and stuff.
That's important. Okay? It turns out that when astronauts work in space, that's actually the thing they fear the most is snapping off bolt heads. Because you only bring so many bolts when you go into space. And when you snap off a bolt head, that's a huge problem. Okay. You know, if you talk to a mechanic understands all these concepts, right? The guy who works on your car understands all of these concepts, but he does it in such a way that because somebody else at some point understood that, well, we have to think about how much torque we're applying, right? They already designed all the equipment so that it probably wouldn't cause him issues, right? But you don't want to be the guy using the equipment. You want to be the guy who designs the equipment. And that's where you're going to need to go beyond just knowing which way to turn the screwdriver, right? Or if it doesn't work, get a bigger monkey wrench. If you want to be the guy that designs the equipment, you have to understand why you need a bigger monkey wrench and how big of a monkey wrench do you really need to give your auto mechanic. Okay, questions? All right, everybody feeling fried?
Yep.
All right. Let's stop there then, and we'll come back on Friday and talk a little bit more about what we can do with this whole torque business. So Friday is going to be fun for you guys. How many of you have to take statics?
Yes.
So Friday, we're going to do statics. We're going to do 1 day worth of statics. Usually I try to do a few days worth of statics, but this semester, 1 is all you get. So we're going to do 1 day worth of statics.
Yay.
And then you're going to take a whole class on statics. Okay. And it'll be fun. We'll have a great time. Okay, that's Friday. So in the meantime, be sure to get cracking on the Wiley Plus. I will take a look at the grading thing and try and figure it out. And have at the video experiments. This latest one is good. I like it. And I will see you guys on Friday.